Look closely at a modern network, and you see a chaotic intersection of physically disparate hardware, copper cables, fiber optics, radio waves, trying to flawlessly transmit data between thousands of distinct software applications. Making these systems communicate seamlessly is a massive engineering hurdle. To solve this interoperability problem, engineers rely on a 7-layer framework known as the OSI model. The core concept here is network abstraction. By isolating specific communication functions into distinct layers, engineers can troubleshoot isolated systems without needing to understand the entire network stack at once. This diagram shows the full vertical structure of the OSI stack, counting down from layer 7 to layer 1. We can group the top 3 layers together. These are primarily the domain of software engineering, handling the direct interactions between user applications and the network. The bottom 3 layers handle the physical and logical transmission of data across the network infrastructure. Sitting exactly in the middle is the transport layer, acting as the critical delivery bridge between the software generating the data and the infrastructure moving it. To understand network engineering, you must track the sequential structural transformations a data payload undergoes as it travels strictly top-down through these categorized zones. When a user application generates a raw data payload, it hits layer 7. The application layer is the only layer directly interacting with user data. It attaches a protocol header to facilitate resource sharing, remote file access, and network management. The protocols operating here are familiar ones: HTTP and HTTPS for web browsers, DNS for domain resolution, SMTP for email, and FTP for file transfers. The payload then drops down into layer 6, often called the translator. Its mandate is to ensure the data is in a readable format for the application layer on the receiving end. It handles data formatting, encryption and decryption, and data compression. This is where formats like ASCII, JPEG, MPEG, and PNG are applied, along with security protocols like SSL or TLS for secure data presentation. Next, the formatted data moves down into layer 5, the session layer. This layer establishes, maintains, and terminates network dialogues between computers. Crucially, it manages authentication and checkpointing, allowing a transfer to resume from a specific point if the connection is interrupted. Protocols operating at this level include NetBIOS, RPC, and SMB, or Server Message Block. Through layers 7, 6, and 5, the data payload has been fully standardized and secured. It is prepped for transit, but it hasn't actually moved across a network yet. The payload drops into layer 4, the transport layer, where it undergoes its first structural transformation. The data is broken down into smaller, manageable chunks called segments. This layer takes responsibility for end-to-end communication between 2 devices. It applies port numbers, for example, port 80 for HTTP, to ensure these segments reach the exact application on the destination device. Look at this matrix. It illustrates the primary engineering trade-off at layer 4, choosing between TCP and UDP for delivery. TCP, or Transmission Control Protocol, is connection-oriented. It guarantees delivery by utilizing strict error correction protocols. Because it includes flow and congestion control to manage the data rate, TCP is the mandatory protocol for high-fidelity tasks like web browsing and email, where losing a single segment breaks the file. UDP, the User Datagram Protocol, operates entirely connectionless. It achieves faster delivery by stripping out error correction entirely. It sends data without flow control. This makes it ideal for speed-dependent tasks like video streaming or online gaming, where speed is critical and dropping a single frame is tolerable. Layer 4 acts as a strategic bridge. It decides exactly how data must travel based on specific application requirements before handing it off to the infrastructure. Dropping into layer 3, the network layer, the segment undergoes another structural transformation. It is wrapped in an outer layer to become a packet. The function of layer 3 is to navigate routing paths between entirely different networks. It determines the best path for data using logical addressing tools like IPv4, IPv6, ICMP for pings, and IPsec. The primary hardware enforcers at this level are routers and layer 3 switches. The packet then moves down to layer 2, the data link layer. A distinct header and trailer clamp onto the front and back of the payload, assembling the final data unit known as a frame. Layer 2 has a very specific mandate: providing localized node-to-node data transfer directly between two closely connected machines. While Layer 3 relies on logical IP addressing to find external networks, Layer 2 uses physical MAC addresses to locate exact devices on the local link. To handle this, Layer 2 is divided into two distinct sublayers: Logical Link Control, or LLC, and Media Access Control, or MAC. The protocols operating here define local networks. This includes Ethernet, the Wi-Fi 802.11 standard, ARP, and Spanning Tree Protocol. The hardware executing these protocols consists primarily of network switches and bridges. To be precise with the infrastructure duties, Layer 3 determines the global path the data will take, while Layer 2 handles the localized heavy lifting of actually jumping from one specific hardware node to the next along that path. Finally, the structured frame reaches the bottom of the stack, where it is converted into physical energy for transmission. Layer 1 is the physical layer. It is responsible for transmitting raw data bits, the zeros and ones, over a physical medium. This requires physical components: copper cables carrying varying voltage states, fiber optics carrying light, or antennas broadcasting Wi-Fi radio frequencies. The hardware governing Layer 1 includes network interface cards, hubs, and repeaters, operating on standards like DSL, USB, and Bluetooth. At this exact boundary, the complex software logic completely dissolves into measurable physical, electrical, and optical energy signals. Now look at the complete end-to-end communication path between two distinct devices. The entire top-down journey we just explored on the sending machine is a process called encapsulation. As data descends, it's segmented at the transport layer, packaged at the network layer, framed at the data link layer, and serialized for transmission. Reaching the destination, the reverse process, decapsulation, occurs. The device takes raw bits at Layer 1 and pushes them upward. As the data ascends, each layer strictly verifies its corresponding header added by the sender, reads the instructions, and then strips that header away. By the time the payload arrives back at Layer 7 on the destination device, it is pristine, perfectly formatted data ready for the application. The primary architectural benefit of this entire framework is strict engineering modularity. Consider a real-world infrastructure scenario, like an enterprise upgrading its entire network from standard copper wiring to high-speed fiber optics. Because Layer 1 is independent, this massive physical upgrade can happen without an engineer needing to rewrite a single line of Layer 7 software code. The OSI model isolates complexity. It guarantees that networks can scale and evolve across an inherently fragmented hardware ecosystem by keeping the software logic and the physical wires strictly independent.